Hello and welcome to this video about the basics of Numpy. Numpy is the main package in Python for handling numerical data. It's like a lot of the things in these videos, it's really useful. Um, Especially for doing like Numpy stands for numerical Python. So it's for numerical operations, so anything mathematical goes to Numpy basically. Yeah, it's built around its container, which is called ND array for n-dimensional array, which can be seen sort of like vectors or multi-dimensional matrices. And the reasons NumPy is so good is it's because all the routines or operations that NumPy can do is built around these arrays, and a lot of the routines are implemented in C code, which is just a lot faster than Python. So that's why it's really good, because it's fast and it's also a lot of the operations are, like you want to do something like calculate the mean, standard deviation, and a lot of more advanced stuff like NumPy has operations to do that instantly, so you can just call a method or a function instead of having to write it up yourself. A list and a NumPy array are some similar in some senses. They look a bit like each other superficially, but they behave very differently, which we'll see. So yeah, the main differences between arrays and lists are that arrays can only have one atomic type as its elements. So you could see if you had a list, then you could have strings and integers and floats in it. But if you have a number array, then you can only have one of those types. So all integers or all floats. And you can also have other types, but since it's numerical Python, then typically you would not need to have strings. Then you might as well use lists, because a lot of the functions are sort of implemented towards having integers and floats. Yeah, as a slice in a NumPy array returns a view and not a copy of the content. So yeah, that means that you can. Yeah, we'll see it later. But it just means that you have to be a little bit careful. NumPy arrays cannot change its size, so you don't have this sort of append functionality. So when you create the NumPy array initially, then you sort of have to decide at the offset how large it's going to be and how many dimensions it's going to have. So NumPy arrays are less flexible than lists, but this allows them to be much more efficient. So some of these things is sort of what allows all the functionalities to be implemented in the C code, basically. Okay, so let's start the basics of the basics. So how to create a NumPy array. I should go back first to say that we've imported NumPy as NP. So we imported the NumPy module and called it NP, which is very common to do. So whenever you see NP in somebody else's code, then assume it's NumPy. Then you initialize an array by typing np.array, and then you can, one way to initialize it is to create it from a list. So here we create an array in one dimension with these elements. You can also create a two-dimensional array, which can sort of be seen as a matrix, and you create it with a list of lists. So you can see here that there's sort of this initial list, and then it contains multiple lists. The way you can see it is as a 4 times 3 matrix. So it has 4 rows and 3 columns. Then we can print all of these attributes or features of the arrays, and you can see that they are both n-dimensional arrays. The data is different. So A we have initialized only with integers. So Python interprets that as its own atomic data type called int32. Just see them as integers. The number is sort of, it's about memory and how large they can be. And these are sort of Python's default integers and float types. So yeah, B we have initialized with floats, so Python calls them float64. We can see that the dimension, and then you use, probably, so to get the type, the type of the atomic elements, or type of elements, you use dtype. To get the dimensions, you use the attribute ndim, number of dimensions, you can sort of view it as. You can also get the shape, which is the shape of the matrix or the numpy array. So here we just have the first A was just like a vector of 10 elements, so it only has like one number, 10, while B was a 4 times 3 matrix. And size is just the total number of elements. So for 10, for A, that's 10, and for B, that's 12, 4 times 3. And you can sort of see the matrix B as a bunch of stacked rows. That's how Python remembers them also. This is not really that important, but Python is a row major language, which means that in memory, this matrix is sort of stored as one long list, and Python sort of remembers them in this order, so it remembers each row. Some languages like MATLAB will remember it by column. Not a huge point. If you want to know more about it, there's like an example of it at the bottom of this notebook. And as I said, slicing a numpy array returns a view, which is a reference to the part of the array that was sliced out. And we can see why that is important in this code block. So we initialize a matrix called A, which is just the same as the one we created above. Then we extract a view, which is the third element to the sixth element. And this view is a slice of A, or a view of A. The slice is a view of A. And then we make changes to V, which will our view into A. And then we can see here down here that A actually also changes. So we initialize it just counting from 0 to 9. But when we change some of the elements, then we're also changing some of the elements in A. That does not happen if you explicitly say that you want a copy of A. So here we create C, it's just a copy of A. And then we change something in C, and then A does not change. So the last statement is this print statements. Numpy arrays can also be created using Numpy functions. So Numpy has like a bunch of functions, and we're not going to be able to go through all of them here. And I don't know all of them. Probably very few people do. You can sort of find the ones that you need when you need them. But these are some of the more common ones. NumPy.ones, so ones in plural, just sort of create a matrix filled with ones. Then you just input the shape you want. So you create a 2 by 3 matrix filled with 1. You can also create zeros, which is just the same, but instead you're creating a matrix filled with zeros. And the default for these functions is to sort of create a float type atomic element type. And I creates a matrix with ones sort of in the diagonal, which can be useful for a lot of algebra stuff. Linspace creates linear spacing between 2 points. So this is really useful for a lot of stuff. What you interpret here is sort of at the same as the range in Python. It's just for integers. So you say here, I want to create a list that goes from 0 to 1, and then I want it to have 6 elements. And then you create a list from 0 to 1 with 6 elements that are evenly spaced. And then we have 2 tips for you. So you can sort of, if you type comma inside a function, then this little box will pop up in VS Code, which is really nice because then you can see, first you can sort of see, okay, what does this function do? Return evenly spaced numbers over a specified interval, and then you can scroll down here, and then you can see, okay, what are the parameters. So the first parameter is the start, so that's the 0 one here. We start here, and then we stop at the second parameter. Then there's a bit more like knowledge about blah blah blah, and then there's the num, which is the number of samples to generate. And here we specified 6. We can see that the default is 50 if you like input no argument. This is super useful when you're using functions, then you can sort of remember the name, but you can't really remember what was that argument. It also actually pops up. You don't even have to write a comma. It sort of pops up automatically whenever you start writing a new function. Like normally if you write something fast, then it sort of maybe disappears. But yeah, sometimes it's slow, sometimes it's fast. But yeah, it's just good to know that you can also just Google these functions, and then you can find the documentation with all this this information, but it's kind of nice to know that it's very easily available. Another way to do it is to just write a question mark before the function, and then you will get sort of the same information, but printed out. Yeah, and then sometimes you might need to open it in a text editor if it's a lot of output, which it usually is for these kind of functions. Yeah, so now we're coming to the mathematical operations, which are sort of the main draw of Numpy, but there are other draws. Yeah, so a lot of it is very intuitive. One thing you have to notice that multiplication, addition, subtraction, and division is sort of element by element for matrices or the ND arrays. So yeah, this sort of it happens. So if you have a matrix here, which is 2 by 2 A, and another matrix also 2 by 2, then when you add them together, then the addition is element by element. So if they have the same shape on the same dimension, then sort of the first element here would just be the sum of the first elements of A and B, and the same with the second element in the first row. That's the sum of these two, 0 and 2, and the same with the second row. Here I've printed out more examples, so it's the same for multiplication, then it's the element, and subtraction and division. The add sign, or snabelag in Danish, is the matrix product, so that's the dot product, from linear algebra maybe. That's also very useful sometimes. Yeah, and that sort of works like you would think, so like the dot product would do. So you do the cross. So the first element here, let's see if I can remember it, is 1 times 2 plus 0 times 2. And then you get 2, and then it's down. You can also see, because this is an I matrix, then it actually just, from linear algebra that this will just be the B matrix, the dot product of A and B. Yeah, that's not important. Let's move on. Broadcasting. If arrays does not fit together, so if they are not of the same dimension, so here we just had two 2 by 2 matrices. If they are not the same dimension, then broadcasting will be applied. And Numpy uses the dimensions that do fit, if they are possible. So this is like the very simple case. If you have a matrix and you multiply it by a scalar, which is like a single value, then Numpy will broadcast that scalar into each of the elements. So if I have some matrix times 2, then the output matrix will be all the elements in the first matrix multiplied by 2. And that's sort of, I think, simple enough to understand and intuitive. But this can also happen even though you have, for example, a vector multiplied with a matrix. So here we have an A matrix, which is 2 by 3. and a B numpy array which is just of length 3. So it had 3 elements. If we multiply those together, then you actually get a 2 by 3 matrix out. So what NumPy does when you say this, then NumPy sort of notices that B has 3 elements, and A's columns are also equal to 3. So NumPy will sort of broadcast this 1, 2, 3 and multiply it to the first row and to the second row separately. So you have here that this is 10 times 1, 20 times 2, and 30 times 3. And then in the next row, then you have the exact same, 40 times 1, 50 times 2 is 100, and 60 times 3. Another example, if you want it on the row dimension, then you can create a C vector, which is sort of basically also just a vector, but it explicitly has 2 rows and 1 columns. This is typically understood as having 1 row and 3 columns. So you just create it as a list of lists, but with 1 element in each list. Then you can see that you get this 2 times 1. And then you can also sort of broadcast this 1, 2 onto A. And then you can see here what happens is that Python broadcasts 1, 2 onto each row. So you can see the first row is 10 and 40 times 2. Then it's 1 times 20 and 50 times 2. So you get 20 and 100. And the same with the last column. Sometimes you want to do this, and Python will tell you that it's not possible. And then you should consider using numpy.newAccess to make it possible. NewAccess also just allows you to be more explicit about how you want broadcasting to be done. So if you want to multiply A and B, where A is a 3-element vector and B is a 2-element vector, or NumPy array, then it's not possible from the offset because they don't have a common length on any of their dimensions. They only have 1 dimension each, and the length is not the same. Then you can use this newAccess to sort of explicitly create an extra dimension, which is just 1. So you turn A into a 3 times 1 NumPy array by writing A and then choosing all of the elements and then comma and then np.newAccess on the axis that you want that to be a new axis. What I mean by that is that you sort of decide that with this colon, you decide, okay, I want all my elements to be in the rows, and then I want them to be a column indicator too. So instead of having 3 comma nothing, then you get 3 comma 1, and you can do the opposite by writing newAccess first, comma, colon, all the elements of B, then you get a 1 times 2 NumPy array. This allows you to broadcast them together, so you can sort of see, okay, this is explicitly what the A newAccess looks like. So you get it into a column vector, and here you create turn B into a explicit row vector. And then when you broadcast them together, then they will sort of band on this common element, and then you turn your multiplication into a 3 times 2 NumPy array. And so what you get out is on this list you just get 1 times the vector. On this column you get 1 times the vector, and then the second column you get 2 times the B column, or the A column, sorry. If you'd done this the reverse way, then you would have turned A into a 1, 3 numpy array and B into a 2, 1 numpy array, and then you get a 2 times 3 numpy array out. On this link you can see a bit more about broadcasting. NumPy has, like, as I've said sometimes now, a lot of mathematical procedures. Here's an example of some of them. You can find the minimum of an array. You can find the index for that minimum value. You can find the mean. You can also find standard deviations and stuff like that. You can also find percentiles. You can also sort the NumPy array here in ascending values. You should note that sometimes, a lot of times, for these sort of simple functions, then NumPy will have a method instead of a function that you can use sort of the same. So here, instead of writing np.mean of a, then you could just write a.mean of a. So that would be a method to the NumPy array, where here you're just sort of calling a function from NumPy, and then you input the NumPy array as an argument. A lot of the times this gives the same, but it doesn't always. There can be like small differences, whether they return a copy or view, for example. And there's also sort of, in NumPy, all the methods that you can find will be available as a function, but not all functions will be available as a method. So we'll tend to stick to functions, but as you get comfortable, then you can use methods as you want. So indexing is how you sort of reference specific elements from the NumPy arrays. In some ways it's similar to lists again, in some ways it's not. So the way you do it is by the squared brackets, and then you input the index you want. If you have like a multi-dimensional array, like here, it's a 2 by 3. Then if you just have one index, then you just choose which row you want to look at, and then you look at the whole row. Typically you would do this explicitly, where you say, okay, I want all of the rows, then you use the colon, comma, 0, then you get all of the rows, but only the first column. All of the rows, but only the first column. So you get these 2 elements here. That's what's printed here. You can also draw a specific element by having sort of integers at both places. So you get the second row and the third column. And you can also use slicing, the same way as when indexing lists, when you say, okay, I want from the second, from the 0, so the first to the second element. So you get 2 rows, that's both rows, and then you want the column 2 and 3 when you say 1 to 3. And here that you get that out as a new NumPy array. Just a 2 by 2 because you've chosen 2 rows and 2 columns. You can also index by sort of logical indexing, which is true false. So you can have a list or NumPy array of true false values, and then if it's true, that would be the same as indexing that element. So here we have 2 NumPy arrays, which is one-dimensional and of the same length, and then we create a new NumPy array called I, which is of the same shape as A and B, because it's sort of created from A and B. We say, okay, we want it to be true if the element of A is less than 3, and this is sort of element-wise comparison. So for each element, we want it to be true if the element in A is less than 3, and if the element in B is equal to 3. So this is what you get here. We're printing the I, And then you get the first one is true because the first element of B is equal to 3, and the second element, or the first element of A is less than 3. And you can sort of compare whole way down. We can see, okay, the last element is false. That makes sense because the element in B is not equal to 3, and the element in A is not less than 3. You can also see at the third element, there we have that this part is actually true, but you have both conditions have to be true at the same time because of this AND operator, and you can see that the third element of A is not less than 3, so you get false out. If you index using this logical list or array of Boolean values, then you can sort of see, okay, you get the elements of A where I is true. You get 1 and 2, and then you get this third last element 2. You can also explicitly get the index numbers by using this numpy.where and then having the I function. And this is sort of explicitly, this is where are the true values or the true elements. You can also use non-zero because true is sort of the Boolean value of 1 and false is 0. So this is where the I list is not equal to 0. Then you get those indexes, which are the same as it being true. So we have the AND operator, which is AND. And then you can also have this vertical line, which just means OR. So there, just either of the conditions have to be true. Yeah. Then a small section about multi-dimensional arrays. So all of the arrays we've seen so far have been one-dimensional or two-dimensional, but you can also have 3 dimensions or 4 dimensions or 5 dimensions and so on. Probably, usually you don't need more than 3, maybe 4. But maybe you'll find a use case for 6, I don't know. And sort of how I view it is as matrices storing other matrices. Because when you have 3-dimensional matrices, then you have sort of, yeah, so you have a space that you can't really see directly. Yeah, here I create an AI matrix, which is 2 by 2, and then I create a matrix or numpy array, which is just sort of 3 AI matrices, so a vector of 3 AI matrices. So you get the shape 3 by 2 by 2. So the last 2 elements are sort of the shape of AI, and then the first element is the shape of this Uber matrix, which is just 3 because it just has 3 matrices inside of it. And then when you print A, then you can see that you sort of get the matrices printed out in a nice way. You can also use this variable list which VS Code has and press on the big A matrix, and then you can sort of see that it shows you the matrix as slices. It explicitly like tells you, okay, this is the first matrix, and these are all the same, but this is the second. They could have different values. Yeah. So if you want to look at them, then VS Code has this optionality for how to look at the matrices. You can also have like not just 1 dimension of storing matrices, but 2 dimension. So here we have a 4-dimensional array. So I create a new sort of small matrix, a 2 by 2 matrix called BI with different elements than the AI, and then I store a 2 by 3 matrix of matrices, and then it gets 2 by 3 and 2 by 2 dimensions. And then when you print it out, it just prints out like the inner matrices, you can call them, separately. You should know that AI and BI, so these smaller matrices, they should all be of the same shape. You can have them not of the same shape. So if I create a 3 by 2 matrix, then I get something out, but Python sort of warns me that I'm doing something bad. and it actually turns the AB matrix into just a 2x3 matrix, which explicitly stores other matrices. So this sort of, it can lead to some bad behavior. So I mean, typically when Python gives you this warning, it means you're doing something that's not a good idea. So you should avoid it. Yeah, so here's a list of good things to know. This is sort of a bunch of attributes of the Numpy arrays and methods you can use, a list of functions you can use, and sort of a list of concepts. Like all of these attributes and functions, you shouldn't try to memorize all of them. It's good to know that there, so the more important thing is to know the logic of Numpy. The concepts are sort of can also be important because you sort of need to understand them. And then you also need to have an idea of what other things Numpy can help you with. Because if you know what type of things Numpy can help you, then when you want something, then you can Google Numpy, whatever you want, and then typically one of these functions will show up, or sort of the exact Numpy function you're looking for, because they have like a bunch of Numpy functions. Yeah, and then as you do that, as you code, you do the problem sets and your projects, then you sort of memorize the functionalities that you find the most useful. So that's basically all from me. These last code blocks is a small quiz that you can take. I encourage you to take, where you sort of have to guess what is the output of each code blocks, and that tests whether or not you sort of understand the logic of Numpy. So yeah, good luck with that, and thank you for watching.